a line segment with magnitude and direction. Now, when we say magnitude, what are we referring to about our vector? Well, it's not the direction, okay? But what about our vector is its magnitude? The length. We're talking about the length. Okay, we're going to say its magnitude, but how long is our vector? That's what we are referring to when we say magnitude. Okay, now, if we were to have a vector has an initial point and a terminal point. Okay. The initial point is where it begins. The terminal point is where it ends. Okay, and the terminal point, that's where that arrowhead is. Okay. Now, if we're talking about equivalent vectors, what's going to have to be the same? The magnitude and the direction. Okay, so I'm going to draw two equivalent vectors here to the best of my ability. Okay, those are equivalent. They have the same direction and the same magnitude. Now, if I were to draw these two vectors right here. These aren't equivalent vectors, but what is true about them? Okay, we could say that their magnitudes are the same because they're the same length, but they're not going in the same direction. They're going in the opposite direction. So we could say that these are parallel vectors. Okay. These two orange vectors that I'm going to draw. So I guess I should say these have the same magnitude. Okay. These two orange vectors that I'm going to draw. What's the same for them? They have the same direction. Okay. But not the same magnitude because they're different lengths. Okay. 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 Now, the work that we do from here with our vectors, we need our vectors to be in a standard position so we can make certain calculations. Okay. It's going to be easier to describe and work with a vector in standard position. If you were to guess what standard position was, a vector in standard position has its initial point at, what would you guess? Yep, the origin. That way, when we have our vector, okay, then we can describe one number for the horizontal and one number for the vertical from how to get from the origin to the terminal point. Okay. Now, if we are not in standard position, then we need to get it there. So there's going to be two different ways that we can write vectors. The first is called component form. All right. If we are not in component form, then we're going to need to get it there by taking our terminal point minus the initial point. Okay. When we have a vector in component form, we're going to have it's going to look kind of like an ordered pair, but they're going to have these chevrons instead of the parentheses. That is how we know that it is a vector and not a coordinate. Okay. So if we have a terminal and an initial point, then to put it in component form, we're going to take terminal minus initial for our x's, terminal minus initial for our y's, and then we will end up with what looks like a coordinate with chevrons, and that's going to represent our vector in our standard form.
What are the two different, like, what does V1 and V2 take?
So those are our two different components. Every time we have a vector, we're going to have a horizontal component and a vertical component. Okay, so like our horizontal component tells us how far do we go over, and our vertical component tells us how far we go up. Okay, when we graph it.
One above it mean the x2 minus x1.
That means if we have a terminal point and an initial point, we're subtracting them in order to get those components. Okay, so let's go ahead and do an example over here. Okay, to the right, and I'll show you what we mean here. Okay, we have an initial point at -2, 3, and a terminal point at -7, 9. Okay, hey, do you notice how V is bolded? Okay, when we name vectors, we name them with a bolded letter. Okay, it's just what we do. Okay, so vector V, we need to take terminal minus initial in order to get this into its component form. All right, so terminal minus initial, we need to take -7 minus -2 for our x component. Terminal minus initial, we need to take 9 minus 3 for our vertical component. So our vector is -5, 6. Okay. So now we can imagine at the origin, this vector is graphed to the left -5 and up 6, like that. Left -5, up 6, and that would be our vector.
So that would be V1 and V2?
Yeah.
Oh, so we take the 2 points. So we do the first equation first and then to get our second answer.
Okay. Now, let's talk about how we actually find the magnitude of a vector. Okay. So I'm going to come over here and I'm going to just draw a vector in general. Okay. And instead of the V1, V2, because I don't really like those right now, let's just talk about A and B. Okay. If I draw a vector and we have a horizontal component of A and we have a vertical component of B, well, what that means is that we are going horizontally A and vertically B. Okay. So first of all, raise your hand if you have an idea on how we would find the length of this vector. Liz, thank you for raising your hand. The Pythagorean Theorem, okay? Also, fun fact, we are going to notate the magnitude with this like double absolute value on our vector name, okay? So like both Zach and Liz suggested, the Pythagorean theorem, side squared plus side squared equals hypotenuse squared, is how we're going to find the magnitude. Well, the magnitude is always the hypotenuse, so we can just solve for it right away. Well, c squared is our magnitude. We're just gonna call it this right here. This is c. But this is how we notate the magnitude.
So we could still put like x squared, right? I'm confused.
So what I did is a squared plus b squared equals,
So you just like substituted it in?
well, yeah, instead of c, we're gonna call it that. And then to solve for it, because we're gonna solve for it every time, we would square root both sides. Okay, so let's come over here to our example. We have our vector v is -5, 6. So if I want our magnitude, then we're just going to take the square root of a squared plus b squared. It's 25 plus 36. So the square root of 61 would be our magnitude. Not so bad, right? Yes.
Do you want us to write it like that, or do you want us to keep it calculated?
Right now, I want you to write it like this, okay? As a reduced radical, okay? Because that will help us for what we're gonna do next, okay? I want you to write it as a reduced radical, okay? There'll be times where you get to use your calculator in here, don't you worry, okay? Now, I want to talk about what a unit vector is. But I guess, first of all, are there any questions on that first example? Okay. Doesn't this feel an awful lot like basic trig?
Yeah.
Right? Okay. I mean, this is the trig unit, right? All right. So unit vector. We did something with a unit circle. Why was it called the unit circle?
Because it was one unit.
Okay, the radius was 1.
Yeah.
So if we're talking about a unit vector, it's got to deal with what number? 1. Okay, what do you think is going to be 1? Okay, a unit vector is a vector with magnitude 1. Okay, so don't write these down right now. I just want you to, I want you to notice something from you, okay? All of these vectors, well, all of these vectors go in the same direction. What do you notice about them? Okay. Okay. Basically, I can multiply a vector by a number. Like I could take this and like double it to get here. I could take this vector and divide it by 2 to get here. I could take this vector and multiply it by 3/2 to get here. They're all like multiples of each other, which means they're going in that same direction. Okay. So we're going to use that fact to help us to force a vector to be a unit vector. So if I want a vector that's in a specific direction, but I want it to have magnitude 1, then what you're going to do is you are going to take 1 over the magnitude of the vector, and you're going to take that number and multiply it to your vector, and you then will have a unit vector in the same direction as B. I'll let you write that down and then we'll talk about it. So we are going to force a vector to have magnitude 1. We'll find its magnitude and we're going to multiply by its reciprocal to our vector that we want it to be in the same direction of. Okay. So what I want you to do first is I want you to come over to this example and I want you to find the magnitude and then compare your magnitude with your buddy and then just stop. I'll show you how to do the rest, but find the magnitude of vector V, please. Find the magnitude compared to your buddy. Just leave it as a radical. Nick, what's our magnitude? Radical 50, radical 58. Do you agree? Okay, radical 58. And let's maybe just remind ourselves that we are taking the square root of a squared plus b squared to get radical 58. Okay. Keep in mind that -3 squared is always going to be positive. Okay, please don't put -3 squared in your calculator without parentheses. Okay, so if we want a vector in the unit vector in the same direction, then we are going to take 1 over the magnitude and multiply it to our vector. Okay. Well, okay, let's think about this here, guys. We already know that 7 - 3 has a magnitude of radical 58. So if I'm taking the magnitude of this guy, radical 58, and multiplying it to this number, what do we get? We get 1, okay? But what I want you to do is I want you to actually, and I want this to be exact, I want you to multiply this through. But is this how I would expect you to leave it? No, obviously not, he says. 7 radical 58 over, excuse me, 58. -3 radical 58 over 58 when we actually rationalize our denominators. But you want to keep them in radicals so we have that exact component form. Otherwise, your unit vector will not actually have an exact measure of 1.
So is that our answer?
That is our answer. Liz doesn't love it.
Yeah, it looks like you can simplify it, but you can't.
Right. Okay. Okay, so we've talked about a vector. Let's maybe talk about the combination of 2 vectors. Go ahead and turn it to the other side of your notes sheet. Okay, let's talk about some things that we can actually do with our vectors. Okay, scalar multiplication. What is a scalar? Scalar is just a number. Okay, it's just a number. So like if I said 2 times the vector 3, 4, 3, 4 is our vector, but 2's the scalar. Okay, and we would say, all right, well, this is 6, 8. Okay, now what happens if our scalar is negative? What's going to happen to our vector? If I have the vector 1, 2, which is this way, and I multiply it by a negative number, what's going to happen? It's going to change directions, more specifically, opposite directions. Okay, you multiply by a negative scalar, your vector will change directions, opposite direction. It'll be parallel, but it'll be in an opposite direction. Okay. Okay, vector addition. Okay, well, maybe let's go to the scalar multiplication. Okay, if I have the vector 1, 2, and I multiply it by a -2, then our vector becomes -2, -4. Which quadrant would vector 1, 2 lie in? The first quadrant. What about vector -2, -4? The third quadrant. It's going in the opposite direction. Okay. Now, when we add vectors together, okay, we are going to put the initial point of the second vector at the terminal point of the first vector. Okay. Now, if I give you a problem, I think it's going to be pretty obvious how to add them together, but I want you to understand what's happening visually. Yes. Yep, that's exactly what it is. Okay, so if I am adding the vectors, u plus v. Okay, well, here is vector u. And then vector v, I'm going to put the initial point of the second vector at the terminal point of my first vector. So basically, here's our first vector. I'm adding the second vector, and then what happens is when we actually connect them, this is our u plus v. That is what is happening visually. Okay. Now, I think that when I give you an addition problem, you're gonna think it's probably the easiest problem that you've done in your homework, okay? But the picture is just as important as the process, okay? You are gonna have to draw a picture, okay? Now, subtraction, if I ask you to subtract a vector from another one, then geometrically, the second vector is going to go in the opposite direction. Okay, we are basically adding the opposite vector. Okay, we're not really subtracting, we're adding the opposite vector. Okay. Now, in the vector world, we have to like name everything different, right? We don't say length, we say magnitude. Okay, we don't say angle, we say direction. We don't say sum or difference. We just say the resultant vector. So when you see that word, that just means you're adding or subtracting vectors together. Don't freak out. Okay, so let's come over here to our examples. Okay. So vector u is 1, 4, and vector v is 3, 2. Okay. Now, I know that you're going to add these together very easily. Okay. I'm not worried about that, but I want you to understand what's happening in our picture. So vector u is vector 1, 4. Okay. And vector v is 3, 2. So from there, I'm going to graph that 3, 2. Okay. Now, some of you think this is silly. Okay. Vector u plus v. What do we really need to do? Yeah, what's 1 plus 3? 4. What is 4 plus 2? Okay, well, our resultant vector is 4, 6. But look, when I actually connect these, I went over 4 up 6. Like geometrically, that is how we get it. Okay, but yes, it's fine to just add the components together. Boom, you're done. Okay. All right, so how about you go ahead and do the subtraction down below, and I'll go ahead and create the picture for us. Okay, here's my vector u. If I'm going to subtract vector v, then that means I'm adding the opposite. So I'm adding -3, -2. Okay, now what do we get out of the deal? What's our vector when we subtract them? -2, 2. Okay, looking at my picture here, if I graph u and then I tack on -v, we end at the coordinate -2, 2. Okay, geometrically, that is what is happening. All right, the last thing I want you to do is 2u minus 3v. Okay, I would suggest multiplying those scalars through first and then subtracting. I'll give you about, I don't know, 20 seconds. Compare it with your neighbor, and then we'll move on. Don't worry about drawing a picture. I just want the resultant vector. Ask me, what did you get? -7, +2. Okay, when we double U, double U, we get 2, 8. When we triple V, we get 9, 6. And so then the subtraction, 2 minus 9 is the -7, 8 minus 6 is the 2. Okay. There we go. Okay. Now, do you remember me saying there's 2 different ways that we can write vectors? Okay. Our standard unit vectors, I, this is not imaginary I, this is bold I. Vector I is the vector 1, 0. Vector J is the vector 0, 1. Okay. So another way to write a vector is to write a vector as the linear combination of vectors I and J. So instead of component form, we're going to call this linear combination form. We would write vector, so you're going to take your horizontal component times vector I plus your vertical component times vector J. Okay. This is the vector 1, 0. So this is only going to the horizontal component. This is the vector 0, 1. So this number is only going to the vertical component. Okay. So if we look at your example just to the right there, we have an initial point at 5, 2 and a terminal point at -3, -1. Okay. Well, let's just talk about our component form first. Our vector, oh, it looks like it's vector U. If we do component form, we're going to take terminal minus initial for our x's, and then terminal minus initial for our y's. So in component form, we have the chevrons, -8, -3. Okay. Now, in linear combination form, we would write vector U instead as -8i minus 3j. So it's like an addition or subtraction of 2 terms. One of them with I, one of them with j. Just another way to write it. Okay. Are you guys ready to do some trig? I feel like we haven't done a lot of trig today, have we? Maybe, I mean, the Pythagorean theorem, right? That's about it. Okay, so we've talked about how to find magnitude. What haven't we talked about how to find? Direction. Okay, the direction is the measure of the angle between the vector and the positive x-axis. Okay, so if I have the vector AB, that means I'm going horizontally A and vertically B. How would we find our direction angle? How could we find that angle, theta? tangent. The tangent of our direction angle is B over A. Okay, and I know we have 2 minutes left of class, but that's plenty of time. Plenty of time. Okay, we have to keep in mind what quadrant we are in. Okay, and your direction angle is always going to be positive between 0 and 360. So let's try this one first. This vector 3, 4. Which quadrant is it in? Quadrant 1. So when we take the tangent of theta is equal to B over A, and your calculator, you can type in, what are you typing in? Not tangent, inverse tangent, because we're solving for this angle right here. Type in inverse tangent of 4 divided by 3. In degree mode, what'd you say? Degrees. Okay, now that was easy. What happens if we're in a different quadrant? Okay, then you're gonna have to adjust. Now, over here, what quadrant is this one in? This is in the 3rd quadrant. Now, when you actually type in the inverse tangent of -10 over -3, you're going to get an acute angle. What do we get? 73.3 degrees. That is not in quadrant 3. That is the reference angle. So if you actually want the angle, then since we are in quadrant 3, here's our reference angle. What are we going to need to do to it? Here's our reference angle. What do we need to do to get the whole thing? Okay, thank you. So our direction angle is actually 253.3 degrees. If we were in the 2nd quadrant, we would have to take 180 minus our angle. You know how to work with reference angles. Your inverse tangent will always give you a reference angle. Just in the nick of time, we got there.